All right, so here we are, class number 2, Pkt5, 12th of February, 2021. And you guys can see the screen, I guess.
Yeah, we can see the screen, but we can't see like you.
All right, I see that. That's odd. Huh. Mute. I do see that you can't see me. Okay, I'm turning it back on and off. Oh, there it is. Okay, I'm back. You can see me now, right?
Yeah, you're good.
All right, good. Okay, now everything's working. So here we go. Let's get through this thing. We got a lot to cover today. I did a Valentine's Day thing today. I always pass out like chocolate hearts, and I didn't have those, but we do this thing. I'll just briefly describe it to you. Where there's a book out a while back, and this is letters from, and I'll put the. I won't have time to sit and play the whole thing for you, but I'll put a link. I'll put a link on there. I'm going to put a note here to add the link. So there's a book out, and it's a book of letters. This is letters from like jarheads, like Marines, all the way, I think it goes all the way like American Revolution, all the way up through like the Iraq War, the first Iraq War. And so it goes Civil War, all this kind of stuff. So these, like the captain or the sergeant will tell his men, I say men because it was men, back in the, now women as well, but they tell them the night before a big battle that where they could certainly die, that they need to write a letter home. And so these are Marines, and reading these letters, and some of these guys didn't make it the next day. So they're writing letters to their wives and to their mothers and to their daughters and sons and fathers, and so it's just the poetry of these Marines it's just heartbreaking, especially if you know they died the next day or so. So I put a letter. One of the most famous love letters ever written was a letter by a guy named Sullivan Ballou in the Civil War. He was a major, and he wrote to his wife in Smithfield about a week before the Battle of Bull Run, the first Battle of Bull Run. And so he sent her this letter. It's amazing. It was featured in a documentary by Ken Burns about the Civil War, and this is the letter. It's about a 3-minute video, so I'll put that link, and it's worth listening to and watching. People don't write letters anymore, right? I mean, you guys text or you message, or you just don't, but you don't write letters to each other. In my attic, my garage attic, I was cleaning that out, and I came across a box I haven't looked at in 20 years, and it's old letters that I wrote my wife back in 81 when I was courting her, 81, 82, 83, 84, when I was courting her, and then letters she wrote back. And so I'll read a letter to her each night from that. It's funny, but it's also, it's amazing that all this stuff that's preserved, because I forgot I used to think like that, or I was that dumb, or, immature, or just the things I would say. But you guys aren't going to have that. So here's my suggestion. That this weekend, I tell you what your mom especially would like, or your aunt, or whoever it is a letter from you, not typed, handwritten, a handwritten letter. And she'll probably frame it. I mean, it means a lot to my generation, because we grew up with letters. And so Jamie and I would argue. We would argue in letters because you couldn't call. Because calls cost money. We were long distance. I mean, I was in Dallas and she was in Stillwater. So we wrote letters. We'd argue. I'd have my argument, and then she would write back at her part. It was crazy. So you'd have these 3-week-long arguments by letter. It's just an interesting dynamic. So that's the Valentine's Day I did with my kids. And of course, this doesn't really change for us. We're still 110 to 1. Well, it will change. Today we may go to 2, but I'm going to start cutting that down to 110 to 150 if the other kids are virtual. Okay. So that'll start Monday, assuming that we get this big snow they're talking about. The test, if we go back on a Wednesday next week, then we'll go ahead and have the test on Thursday. For you all, it'd be Friday. And if we don't, though, if we go back on Thursday, we're going to push the test back another week. But got to do it. I gave the last set of dogs today. The next one's dinosaurs. There's your homework sniper. We'll get to that in a minute. So this is where we left the front of 5.1. And by the way, now I have all the sheets, and I passed out the packets to all the kids. And I also put all the PDFs now are on both on the Facebook group in Unit 5, I think it is, or Unit 4, one of those. It's PDF unit. It's also on Canvas, and they're all PDF, so you can print them all off if you have a printer. I will go ahead and put some copies in the front porch, even though I'm not requiring front porch anymore. But you know, you can sometimes you just don't have printers, so you have to somehow do the problem. So I'll go ahead and put some, when we're done here, I'll put some of those packets on the front porch. And it's a terrible day to try and come over. So maybe just for now, write them down in your notebook. And then when you get a chance, when the weather clears up or something, come by and pick it up, or else just go to a printer and print them off. Okay, so I handed out the packets to all the in-person kids today. And then we remember we talked about yesterday, I said we have these, I have these red balls that we hang on the string and we attach them to a board. And so today I took a picture of it before I left. And because we talked about this today. This is showing type 1 projectile motion. And this is one ball every quarter second on a certain planet, not the Earth. As that ball, we shoot that ball horizontally, and this is the ball as it falls. So every one of these represents a quarter second. So initially it comes out of the barrel, then that's a quarter second later. There's half a second later. There's 3/4. There's 1 second later. Okay, so it's like a strobe light looking at this, and the strobe light comes on every quarter second. And here's how the ball falls towards that planet. This is called type 1. So this is type 1 projectile motion. Type. And today we'll just do problems on type 1. And we'll do a little bit Monday as well. Then we'll go on to type 2A. This is type 2A. So type 2A, type 2A is here. And type 2A is, once again, you can also use it with the strings. But now you just put an angle to it. So in type 2A, and we'll get to this more Monday, Tuesday next week, but type 2A, that's shot off at an angle at a certain height, and it lands at that same height. So in type 2A, delta Y is 0. So that's the break you catch with type 2A. In type 1, the break you catch is V naught Y. V naught Y is equal to 0. So it helps out with the equations. Type 2A, it helps out with the equations because delta Y equals 0. We'll get to that on Monday, Tuesday next week. And then there's type 2B. Now type 2B, there's two kinds of type 2Bs. Type 2B is it's shot off at an angle, but it lands above you. So now you do have an ultimate delta Y. And it could land above you like this, or it could land, I keep doing that. Oh my goodness. It land above you, or it could land below you. And this is also type 2B. Now type 2B, you don't catch any kind of breaks. You got to go full hog on the equations there. All right. So those are the kind that'll keep us busy for this week and next week for just looking at this stuff. And there's all kinds of equations and stuff that go with it. So this is good though, because this gets us in the physics of all sports. Any kind of basketball, baseball, golf, it's all projectile motion. And then we brought up Pboy. This is Pboy, and I can take Pboy, I found him in a truck stop one time, there was a real Pboy, and this guy here, you pull those blue shorts down and he pees, and so we did that class today. You can look at all in a shatter. You can look at the different types of projectile motion. But I did this to honor the real Pboy. There was a real Pboy at Norman High School. It's about 10 years ago, maybe 15 years ago. But Pboy, I would send my boys to the bathroom. You know, they had to go to the bathroom, right? So they would just go to. Back then, you just kind of grabbed it. It was pretty casual about going to the bathroom. Just grab the hall pass or grab the whatever I had there for the hall pass. But then they kept coming back complaining that all the toilet paper was wet. And so, but then we did a further inspection, we found that it was urine. So Pboy, this guy, would go and then pee, instead of peeing in the toilet, he'd pee on the toilet paper. And he wasn't satisfied with just doing that. He would stop, go to the next stall, recalibrate, and pee again. And he got it so that all the toilet paper in all the men's stalls in the science building were urine soaked. And so my kids would have to go to the main building, and it was a pain. And we started doing lookouts for Pboy, and kids had to sign out. Well, then somehow, I don't know how he did it. He might have had an accomplice or two, but then it turns out that all the toilet paper in all the boys' rooms of Norman High became soaked with urine. So he either drank a lot of water, I don't know what it was, but this guy was a maniac. And so guys were getting pissed because they couldn't. So we had to get our own toilet paper and then make sure they took it with them, came back. We still have that, by the way, in the room. So yeah, so it finally stopped after about 3 weeks of this, of terrorizing Norman High School. Either he got tired of doing it or they caught him. We didn't have cameras back then. So then about a month later, not to be outdone, we had Pboy. And Pboy was a whole nother level. He was quite the artist, let's put it that way. And they finally caught him after a couple of weeks. I don't know what happened to him. They took him off to the state hospital or something, because that's a little wacko. So anyway, that's where the whole Pboy came from. Now back to projectile motion. So here, I like this slide, and I'll put this screenshot in the screenshots. That's from last year. But if something's going in type 1 projectile motion, as it goes along in the X direction, now we are making the assumption with projectile motion, we make the assumption that air drag is negligible, okay? Air drag is negligible. So that in the X direction, this delta X, this is one ball again, one ball, and this is the projection along the X and the projection on the Y. But we're making the assumption that delta X every time is the same. Because of Newton's first law, a body in motion stays in motion with the same velocity. So horizontally, there is no, unless acted upon by an unbalanced force, there is no unbalanced force in the X direction if there's no air drag. Or you could say it's on the moon, right, with no atmosphere. That's what we talked about yesterday. But in the Y direction, of course, there is gravity. And so the ball will fall 1 unit of distance in the first second, let's say 3 units of distance in the second, 5 units, et cetera, and that's where you get the parabolic shape. When you add up these two together, you get a parabola. Now, what I did was, this is what I was showing you yesterday. I did this one summer, a couple summers ago. I kind of work on it every year a little bit. But I looked at a ball going off a table, and I said, okay, if I scoot that ball along with my hand at 8 meters a second, then just let it roll off the table, in the first second, it's going to go 8 meters a second, right, in the X direction, but it's going to drop. Now, this is assuming I'm not on Earth. I'm on some planet or moon that has no air drag, but has a influencer or a G, quote G, of -2 or not, G's not negative, but negative G, in this case, negative G would be equal to -2 meters per second per second. So it's a field force. And so notice those green arrows are everywhere because it's a field force, all constantly down. Well, that was going to influence this ball that rolls off the table. And in the first second, it'll fall. It'll be moved. These are velocity vectors. It'll be moving at 2 meters per second, negative 2 meters per second in the first second. In the second second, it's going -4, then -6, then -8, then -10. So it's gaining, linearly gaining 2 meters per second every second. And so if you go 8 seconds worth, that's what it'll look like. Now, when you squint and look at that blue curve, it looks parabolic. But when you zoom in, you see, wait a minute, that's a series of vector arrows, okay? And then I went and took it further. I went all the way down to 20 seconds. And you go, why would you do that? You must be obsessive compulsive. Well, I find it relaxing, but I wanted to actually go out to a minute. So I'll probably do that this summer. I want to keep going. I'll make it 3 times that size. But I'm looking at the arrow, the velocity vector. And so the first velocity vector, after 1 second, the velocity vector looks like that first arrow. But in the second, notice because the X part of it doesn't change, but the Y part gets getting bigger and bigger. So that makes the velocity vector itself get big, the hypotenuse get bigger and bigger. Well, this is after 18 seconds. So for this last one, we're looking at 18 seconds into flight, assuming it could actually fall for 18 seconds. That has to be a very tall table and no air drag. But if that were the case, and then so my thinking was, how much will this blue hypotenuse start to look vertical, after a while? And it never will look vertical totally, because you'll always have that, you'll always have the this guy. You're always going to have the horizontal component, but the limit on the vertical component is going to be speed of light. Now, of course, you get close to the speed of light, then mass changes, it gets more complicated. But let's say, I don't know, 1,000,000 miles an hour, whatever. It's going to still be not going to perfectly be vertical. It's going to be maybe a 0.0001 degree, shift from verticality. But anyway, I guess this summer I'll go out to a minute and see what happens. See how it looks. I'm a visual guy. So the way I do physics, and here's the first second. And I think this summer I'll take this and probably cut it down to 0.05 seconds. Look at it. Now, so I want to look at it in the first second of motion, and I want to look at it in a minute's worth of motion. Because this is how my brain works. I got to see the vision, and then I start to write. It makes me write about what I'm seeing, and then I conjecture and where this is going to take me, and I start talking about photons and speed of light and space time, and all this comes out of this. So it's my thought process, but it starts with a picture. It starts with a drawing, a graph, and then you start taking this to extremes, and you say, what is this graph telling me? So I think I can make a case that I study motion more than anybody else in Oklahoma. Because if you're a physics major, if you get a PhD in physics, no one's going to pay you to research motion, right? This is Newtonian stuff. They're going to pay you to come up with new computer chips or quantum or whatever. So you don't really, they blow right past all this stuff. Well, I do it every year with you guys, right? So I feel like there is a book in this. There is, I know it's analyzing to the nth degree, but I don't know. I find it interesting and relaxing. You guys play video games? I take projectile motion out to the 60th second. Okay. So now, I'm going to hold off on the front of this one right here. I'm going to hold off on that one till Monday, because we started to get into it in first hour and they were getting confused. So I said, okay, let's just back off. Let's go on and work a couple of problems. That worked out better. So now we're going to work a problem. So you'll need the back of 5.1. Hopefully you have the PDF or you have it open on another screen or you split screen or something, because we're going to work on this guy. So what we did today in class, basically after the Valentine's Day thing and all this other stuff, is and then me talking about that, is we did number 2 together on the back of 5.1. We did number 3 on the board, okay, and then 4 and 5 I assigned as homework, and they get the stamp for Pkt5 is a dinosaur, so they get dinosaur stamps on these. So let's work together. What time's 1:34? Okay, so let's work together number 2. Okay, so find pencil, paper. If you don't have the actual number, if you don't have it printed off yet, and you can't find your screen, just look off this screen. And on a piece of paper, let's try and work this problem. It's projectile motion, type 1. All these are type 1, okay? Projectile motion. So you start working it. I'm going to actually, so they don't sit down and watch us work, I'm going to hit pause so we don't bore the people to death. Resume recording. Okay, let's go back. Oh, sorry, I'm going to repeat this. We were talking off air. The upshot of the discussion was, or me talking was, that if there's no air drag, then there is no slowdown of motion in the x direction, and therefore v naught x is v2x, is v3x, is v4x, v final x is always the same. For that drawing I showed right here, for this drawing, notice that the 8 never changes in the x direction, that component of the triangle. So therefore, acceleration, one thing that comes from projectile motion is a sub x equals 0. So when you're doing, so you think, oh my goodness, I need 6 equations to work projectile motion problems. But because of that, a sub x being 0, in the x direction, it's just basically red. So all we got to worry about is the red equation in the x direction. And then we still got to worry about the 3 blue equations because there is gravity in the vertical. But like I was telling them earlier, about 75% of the time, you only really use the second blue. Okay, thank you, Eric, for saving my life there. I'm going to hate to have to come back and do that all thing again this afternoon. So this, if there were no gravity, according to Newton's first law, that would just keep going and going and going. That bullet comes out of a rifle. But then it says that no, it actually ends up hitting 3 inches below where it aimed at. So it drops. In that 100 feet, it drops 3 inches. And I'm not going to do this to scale. Okay, this is not to scale, not to scale. Meaning that, this doesn't it's not really 100 feet through. All right, so this is delta y. Delta y then is -3 inches. And delta x is 100 feet. Now, when you connect those up, you don't, as I saw some students do today, you don't do this. You don't connect those up with a straight line, okay? I know I was doing it when I was showing you, but this actually is a multiple seconds. So this is actually, it's a parabola. So you don't do that, you take that away. And this is hard to draw, but you got to draw a very long and it doesn't drop very much parabola. Something like that. So that's the path. That's the actual path of that bullet. Okay. Now, what else do we know? Oh, got to be careful here. What is your G going to be?
32.2.
Right, 32.2. Thank you. There's your point. Feet per second squared. Your delta y is -3 inches, but why would that get you in trouble?
Because it's not in feet.
So if your G's in feet per second squared, you're going to have to make your delta y in feet. That's no big deal. That's a 1/4 foot. So your delta y is negative 0.25 feet, quarter foot. So I'm going to take that so I don't end up using, I'll get rid of that. Okay, now I think we're ready to start. And when you're doing projectile motion problems, you make a T-chart. Okay. And then I want my X part and my Y part. So the Y part's always more complicated because we have acceleration in the Y. So this will be my Y equations. This will be my X equations. And so we already said that in the X, it's simply delta X equals Vx times T. I'm trying to solve for Vx. So Vx is equal to delta X over T. And we do, my modus operandi here is I go as far as I can in the X, and then I go to the Y. Sometimes it helps, as you'll see in later problems. So I'm going to move this over a little bit. So then if I plug in as much as I can, that's 100 feet over time. And I can't find time in the X direction with what I'm given. So that's why I go to the Y. You go to the Y to get time. Well, okay, so let's go, like I said, 75% of the time, your default should probably be the second Y. Delta Y, I mean, the third Y doesn't really help if time's involved, right? You don't use third Y. So delta Y equals V naught YT minus 1/2 GT squared. Ah, but what huge break do we catch with type 1 projectile motion? How has my life become simpler?
V naught 0.
So that's why type 1 are the easiest kind of projectile motion problems. So your second blue equation becomes delta Y equals negative 1/2 GT squared. Okay, so now I'm going to have to solve for T because I need T. My strategy here is to go ahead and solve for T, then plug that T back in here, and then I'll have my Vx in feet per second. Then at the end, I'll convert that to miles per hour. So now we have to do the old algebra 1 trick and isolate that T. And when you do that, you go ahead and multiply both sides by -2, divide both sides by G, and take the square root. So when I do all that, I'll get -2 delta Y over G. Now, one of my first hour students was quick on the draw, and he said, he woke up, he said, wait a minute, you can't, Mr. Ask, something's wrong, because you can't take the square root of a negative number. We don't deal with imaginary numbers in classical physics. And so I agree, but why is that not a problem in this situation?
Because the delta Y is also negative.
Good. And you didn't fall for it. Every class so far, somebody's jumped in there and said, because G is negative. No, 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 G. And I yell at them. I scream at them. No, I don't. But I tell them, I said, no, you fell for my trick. Delta G is always, always, always positive. It is a magnitude. It cannot be negative. So you're right, though. Delta Y is negative. You go, what, always? Yes, in type 1. If I push pass a basketball like this, push pass it, right? I'm not going to push pass off your chest, push past a basketball, and it ends up above me. It's always anything that comes off horizontal, a bullet, whatever, a baseball, anything that comes off horizontal is going to land below. Your delta Y will always be negative. And if you didn't have that negative there, you'd be in big trouble. So the delta Y has to be negative in a type 1 projectile motion. Okay. So let's go back. So that is, so plug some numbers in here. That is the square root. You're probably way ahead of me here. that is the square root of -2 times -0.25 feet divided by 32 positive, 32.2 feet per second squared. Okay, somebody punch that in. What do I get for time? I don't remember. Notice you'll end up in seconds. Feet's canceled. 1/1 second is second squared. Squared is second squared is second. So it's the units work out. But what do I end up in? You guys gonna make me do it? Come on, man.
0.125 if you round up to 6.
Good enough. Good enough. So 0.125 seconds. I think that does sound familiar. I think Natalie got that in third hour. Oh, that's not. I'll box it. It's not my final answer. Now I got to take that 0.125 and I got to come back and stick it into. This is how you do a lot of projectile motion. Now I got to stick it into that T right there. So I'm going to go to the next problem here. But then Vx is equal to 100 feet over 0.125 seconds. And that ends up being, what do you get? 800 and something. Well, it'd be 800. Hold it. Yeah, it should be 800 because that's 1/8. 800 even, yeah?
Yeah, you're right. It's 800.
Yeah, 800 even. Okay, so I think they were getting different answers, but they were rounding time to like 0.13 and stuff. Anyway, the way it is here, we're going to go with 800 feet per second, but it says in miles per hour. So now we got to do the old quick unit analysis here. 800 feet per second, 3,600 seconds in an hour, and then 5,280 feet in a mile. And the answer shows it as, if you go down to the bottom of the page, the answer shows it as 545. Come down here, 545 miles an hour, give or take. You won't get that here because we're using a slightly different number. But that's so, well, because this is I better do it right. So this is recording this 800 times 3,600 divided by 5280. Oh, okay, 545. So 545 miles per hour. You go, wow, that's pretty fast. Actually, that's slow for a bullet. Most bullets come out at about over Mach 1, so 740 miles an hour. So more like some bullets come out at 1,000 miles an hour. So this is like a 22, pretty slow bullet. Okay, so that's all. Here's my work that I'll post. Here's my official key to that. Red is for red equation work. Blue is for blue equation work. And then I left that in red, but I showed the conversion at the bottom. So I'll post this. It's all nice and neat and all kind of not thrown together. Now, what time we got? I got a few minutes here. The next thing we did in class, we had about 7 or 8 minutes left to go in class at this point. And so we took 3 and went to the board. So we went to the board and worked that one. They worked that one. And I didn't hear a lot of gnashing of teeth. So it's pretty much the same problem. This time you're given something different. Here you're given delta y. Notice that delta y will be -8 meters now because it's falling below you. It's coming off horizontally. This is almost the same problem. The horizontal distance is 10 meters. So there's your delta x. And the question is, what's your initial velocity of the ball? So pretty much the same problem. A little easier because you don't have to do anything. This is actually an easy problem, number 2. So I'm going to let you work that one on your own, and you should get 7.83 meters per second. No one complained about it, so I think they were getting it just fine. But so for you all, I guess your homework is 3, 4, and 5, because I want to have this thing done Let me help you out on 4. But I want you to have this done by Monday, so we can move on. I want to move on. I want to do maybe one type 1 and then move on. Oh, you know what? We still got to go back and figure out the gravity on that planet. We'll spend some time doing that. Yeah. So have all these at least attempted. But let me show you this on 4. Last thing here. Number 4 is a weird. It's not a hard problem, but the hardest part about 4 is drawing it correctly. And so if you read 4, there's all these distances involved, and I'll go ahead and put the screenshot in the Facebook, so you'll have this to look at when you're doing the homework. So just, if it doesn't make sense, check out the screenshots, okay? Other questions on these things before we stop sharing the screen?
I have a question.
Yeah.
So on number 3, it says the student threw the ball horizontally out the window 8 meters above the ground.
Mhm.
So since it's above, would delta y be positive instead of
No,
negative?
because, okay, it's a great question. That's worth a point, because the thing is, so you throw the ball out the window and the origin is always the hand. So when you're like plotting it, the hand is the origin. So that means that the ball ends up going like this. And so it's in the 4th quadrant, essentially. So delta y then equals negative 8 meters. Okay, that's how you show it, negative 8 meters. If it was positive, then you'd end up with an impossible situation because it wouldn't rise above, you know. Okay, good question. Anybody else? I'll stop sharing. So this weekend, print stuff off if you need to. You can stop by the porch. Don't risk life or limb. Hey, when you come to the porch, it could be slick. So don't, I'm saying, I'll maybe throw some salt on there, but wood isn't slick, but the brick steps are. So I just seen you not, because I don't want anybody to fall over. But if you just cannot get these things printed off and otherwise, then, I'll have some for you. Okay. We'll be on Pkt5 for a long time. We're not going to test on 5 till like spring break, or so. You got plenty of time, but you can wait till the weather clears up before you come by, or just don't come by at all and just print them off. Okay. Well, you guys are real good about getting on Facebook and asking questions when you got them. So have a good weekend, folks. And I'll see you Monday. Bye.